The Hi everybody. The next section that we're going to look at is section 5.6, and in this section we'll kind of put all the techniques together and help you determine which techniques to use and which ones not to use. So there will only be two objectives in this section, namely determining the appropriate probability rules to use, and then two, determining the appropriate counting technique to use. So let's look at the first situation. So as far as finding the probability of an event, you can kind of go through this flow chart. Ask yourself, are you finding the probability of a single event? Either yes or no. Are the events equally likely? If yes, then use this. And if the events involve or, and, or at least, then you would follow these branches. So let me just jump in and do some examples here. We'll kind of see how this works, and you don't necessarily have to, follow this flow chart in a hard, fast way. If you sort of see how to do the problem, you don't have to use the flow chart. But let's look at an example, and here's just the top half of the flow chart and the bottom half. So as you guys may or may not have seen in the game show Deal or No Deal, a contestant is presented with 26 suitcases that contain dollar amounts ranging from a penny to $1 million, and the contestant must pick an initial case that is set aside as the game progresses, and the amounts are randomly distributed among the suitcases prior to the game. Consider the following breakdown, right? So this would mean 8 of the suitcases have between a penny and $100, 6 have between $200 and $1,000, right? And then like 7 have between $100,000 and $1 million. So the probability of this event is not compound, so decide among the empirical, classical, or subjective approaches. So each prize amount is randomly assigned to one of the 26 suitcases, so the outcomes are equally likely. And from the table we see that 7 of the cases contain at least 100,000, so let's let E in this case be worth at least 100,000 and compute the probability of E occurring. So the number of possible outcomes, again, you have 26 suitcases. You could choose 7 of the 26, right? And then I guess you're not counting the initial suitcase that's set aside here. So the probability in this case of the event E would be 0.269. So that would mean that the chance of a contestant selecting a suitcase worth at least $100,000 is 26.9%. So basically in about 100 different games, we would expect that about 27 games to result in a contestant choosing a suitcase that's worth at least $100,000. So we're kind of, in this case, I guess following the top branch, right, and we're asking whether this is empirical or not if you're following the decision tree we were looking at earlier. Let's look at another example here. According to a Harris poll in January of 2008, 14% of adult Americans have one or more tattoos, 50% have pierced ears, and 65% of those with one or more tattoos also have pierced ears. What is the probability that a randomly selected adult American has one or more tattoos or pierced ears? Right, well, so the probability of a compound event involving, in this case, involves and so let E be equal one or more tattoos and F ears pierced. So we're asked to find the probability of E and F, and so the problem statement then tells us that the probability of F is 50%. The probability that the person has their ears pierced given that they have one or more tattoos. We were told that we're given that in the problem. That's 65%. So because these two things are not equal, the two events are not independent, so we'd want to use the general multiplication rule. So I guess just, if you go back to the diagram we were talking about here, right, you'd want to sort of follow the bottom branch right down to the, do the events involve the word or and or at least, and it, involves the words and then so, are the events independent, then you'd choose no, you'd go to the probability rule on the bottom. So again, I don't know if when I do these problems, I don't know if I always follow the decision tree thing, but if it helps you, you can certainly use it. So the chance of selecting an adult American at random who has one or more tattoos and pierced ears is about 9.1%. So that brings us to objective 2, which is determining the appropriate counting technique. This would be from 5.5. So the last couple examples we're looking at, we're taking problems from 5.3 or 5.4. So here's sort of the flow chart you'd want to use for this, right? Are you making a sequence of choices, either yes or no? Does the arrangement matter? If no, then you use a combination. If yes, then you'd want to use a permutation. Again, you might want to use the multiplication rule of counting or use a tree diagram in this case. So let's just do some examples here. And again, you don't necessarily have to follow this flowchart if you can sort of determine what the answer would be on your own. But let's say that the Hazelwood City Council consists of 5 men and 4 women. How many different subcommittees can be formed that consist of 3 men and 2 women? So the sequence of events to consider here is, right, you select men and select the women. Since the number of choices each stage is independent of the previous choice, we use the multiplication rule of counting. So I guess we'd want to go along the top branch of the decision tree there. So that would be the number of ways to pick 3 men times the number of ways to pick 2 women. So that would be 5 choose 3, or 10. So to select the women, we have to consider the number of reigns of 3 women taken 2 at a time. And so that would be 3 choose 2, which would be 3. And so the number of subcommittees you could form then would be 10, the answer here, times the answer here, 10 times 3, or 30 possible subcommittees. And notice we're not, calculating probabilities here, right? That's what we're not using the previous decision tree, right? We're just counting. Let's maybe look at one more example. Let's say in February of 2008, right, the Daytona International Speedway hosted a race. And this was touted by many to be the most anticipated event in racing history. The race carried a record purse of $18.7 million, with 43 drivers in the race. And how many different ways could the top 4 finishers occur, right? So again, I guess I would just use the rule of counting in this case. But you could maybe use permutations. So again, you have 43 choices for the first place winner, and then the first place winner can't be the second place winner, so that you leave you with 42 for the second, 41 for the third, and 40 for the fourth place, which would leave you with this many possible winning combinations. I guess you could also use this and think of this as a permutation. So you would think of this as 43 permute 4, which would also give you the same answer. Okay, well that pretty much finishes up that section. The last section is optional, and it's in the CD that comes with your book. If you want to read it or not, we haven't talked about what are known as Bayesian statistics. We've been looking mainly at Fisherian statistics. But if you want to learn more about Bayesian statistics, you can take a look at 5.7, but we're not going to cover that. So, all right, as usual, if you guys have questions or anything, let me know, but this should pretty much wrap up chapter 5. So the next chapter we'll look at is chapter 6.